We're going to revisit the problem that we saw in the last video because I want to show you an alternative path. You'll notice there's something kind of maybe cumbersome going on with the coefficients. Like for y of t, we had a c1 and a c2, and that was fine. But for x, we have this negative 2/3 c1 minus root 5 over 3 c2. And the thing is that the c1 and the c2 have the same meaning every time we see them. And the coefficients on cosine in the x function and the y function are coupled together because this was a system of equations, right? They were coupled together by the system. Now, what we found is the solution, and this is done. But I want to go back over something different. I want to use a different technique, actually. And the different technique starts after we find y of t, because I've got to talk about this nuance thing here. Just to remind you, what we did was we encountered the original system, we multiplied, operated, all that stuff to get rid of x, and then we were left with y, and that's how we found y, right? So suppose we had done all that, but now we want to go back and eliminate y in order to solve for x. Sometimes that's actually a necessary thing that we have to do. So I've reproduced the system here, and in front of us we have our solution y. We're going to pretend we don't have x right now. And now we want to eliminate y. In order to do that, we can, I'm going to again number the equations 1 and 2. We can apply the operator d plus 2 to equation 1 and subtract from that d minus 1 operating on equation 2. That'll give us the same y terms but opposite signs. Applying these operators looks like d plus 2 d plus 1 acting on x plus d plus 2 d minus 1 acting on y is equal to d plus 2 acting on 2. Now remember that d is the derivative of 2, so really this just becomes 2 times 2, so the right hand side is just 4. Applying the negative of d minus 1 to equation 2 is going to give us negative 3d minus 1 acting on x minus d minus 1 d plus 2 acting on y is equal to that negative in front of the d minus 1 times negative 1 is going to be a positive. So we have d minus 1 acting on 1. And so that right hand side equals negative 1. We see adding is going to get rid of the y terms. That was the whole point of all of that. And then looking at the x terms on the left hand side, d2 plus 3d plus 2 minus 3d plus 3, all acting on x, that's our left hand side, equals 4 minus 1, so 3 on the right hand side. 3d's are going to subtract out, and we have d2 plus 5 acting on x is equal to 3, giving us an auxiliary equation of m squared plus 5 is equal to 0, and roots of m equals plus or minus I times the square root of 5. So the complementary function for x is, we've already used c1 and c2 when we found y. So, and that's part of the point of this, is what happens when we have c3 times the cosine of the square root of 5t plus c4 times the sine of the square root of 5t. You've already seen how to handle the particular solution because of the non-homogeneous equation. So instead of finding x sub c, I'll just tell you x of t, you can confirm this, has the constant 3/5. Okay, great. Now we've got two solutions. I'll just reproduce this one down here. And we may think, hey, everything's fine. However, in all of this process, the highest order differential equation we ever had was the second order. We can't have 4 constants when there was only a second order differential equation running around. But the other thing is that these constants are not represented in terms of each other. There's no coupling here. This is supposed to be from the same system. So we need to figure out a relationship between C1, C2, C3, and C4. For that, we have to go to either equation in the original system, substitute our solutions in, and then see what we end up with, okay? 3x plus d plus 2 acting on y equals -1 is as good a candidate as any. And if we take x of t and y of t and put them into equation 2, what that'll look like is 3 times c3 cosine root 5t plus c4 sine root 5t plus 3/5 plus d plus 2 acting on c1 cosine root 5t plus c2 sine root 5t, I'm not going to fit it in, minus 7/5 is equal to -1. Oh, parenthesis there. Wanted all of that on one line. All right, if we now distribute the 3 into the first set of parentheses, and then apply the d plus 2 operator to the second set of parentheses, then we get 3c3 cosine root 5t plus 3c4 sine root 5t plus 9/5 minus c1 root 5 sine root 5t plus c2 root 5 cosine root 5t plus 2c1 cosine root 5t plus 2c2 sine root 5t minus 14/5 equals 1. See, this is now coupling our solutions for x and y into one of the equations. Now, what we're going to do is note that we have cosine terms and sine terms and constant terms on the left side of the equation. On the right side of the equation, we just have the constant term 1. So if we gather together all of our cosine terms, from the left-hand side, we have 3c3 plus c2 times the square root of 5 plus 2c1. On the right-hand side, there are no cosine terms, so that equals 0. If we do the same thing with the sine terms, then we get 3c4 minus c1 root 5 plus 2c2 equals 0, again because there are no terms on the right-hand side that have the sign in them. And then for the constants, we have 9/5 minus 14/5 on the left. And I see an error that I made over here because the right-hand side was supposed to equal -1, and that negative 14/5 plus 9/5 is indeed -1, so we can see that the solutions work with the differential equation. But what we have now is C3, C2, and C1 all in the same equation. So we have a connection between C3, which was the constant that we got in x, and C1 and C2, which were the constants that were present in y. In the sine equation, we've got C4 in relation with C1 and C2 in the same equation. Solving for C3 gives us that C3 is -2/3 C1 minus square root of 5 over 3 C2. And solving for C4 is going to give us square root of 5 over 3 C1 minus 2/3 C2 equals C4. Now, if you look at the other solutions that we came up with, the cosine term has a coefficient of -2/3 C1 minus square root of 5 over 3 C2. In the second round, we found we represented that coefficient using C3, and here we have C3 equaling the same expression. So you've now seen two paths we can take. One of them is eliminate one of the functions and then find the other function by isolating and substituting, or eliminate one function and then separately eliminate the other function. But if you do that, you've got to put them both into one of the original equations so that ultimately we're expressing the solutions in terms only of the number of arbitrary constants that matches whatever the highest order was of the differential equations that showed up in the process.